calculate the work that it does, and basically I just have to multiply by delta x. P1 minus P2 times A is the force, and times displacement is the work. That's my non-conservative work. All right, so now let's go ahead and just go to plugging in everything. So my initial kinetic energy, that's in section 1, so 1/2 mv1 squared. And now that I've firmly established that the kinetic energy can change because of the water around, let me not be so restrictive as to only let my pipe run horizontally. Let me leave that potential energy term in there in case I might want to tilt my pipe or something. So let me include that. So we might be able to actually use that. And then I'll go ahead and plug in my newfound non-conservative work term. And then, of course, I reassess my mechanical energy at the end. Now, you could certainly use the equation just like that, and you wouldn't be wrong, but it's not the most user-friendly form. First of all, it cherry picks a particular chunk of water within the fluid, and we want to talk about the fluid as a whole. So we don't want to have to pick like a projectile within the water, the greater water. We want to just talk about the water as a whole. Now, if we shuffle a few things around, that's exactly what we can do. Let me show you. So first of all, when we say A, what we actually mean is that the area of the back side of this object and the front side as well. So basically, we're looking at how the water is being pushed from behind and being pushed from ahead. Now, if you're entirely within section 1, nothing happens because the pressure is the same on both sides. So the pressure is P1 here, and it's also P1 here. So they push equally, and of course, if they push equally, they might as well not have even bothered. So there will be no non-conservative work at that point. This thing will just stay coasting along at a uniform speed in section 1. That also applies by the time you exited and you're entirely in section 2, because then you have pressure that's in section 2 on both sides. So where all the action happens is when you're crossing over this threshold. So you're half in section 1, or partly in section 1 and partly in section 2, because that gives you the opportunity to experience different pressures on your back versus your front. So when you're crossing over, I guess let me redraw it here. When you're crossing over, you have pressure 1 here and pressure 2 here. Now, if you're wondering, how did I know pressure 1 was bigger? I certainly drew it bigger. It's because I remembered that the force always points towards the lower pressure, right? And I already know that the overall force points to the right. So this is a competition between the higher pressure in the back and the lower pressure in the front, and the higher pressure in the back is going to win that, right? So the force points towards where the lower pressure, the larger pressure wants it to. So what we have is that pressure P1 is pushing on this area A, and pressure P2 is pushing on that area. So they both try to get into that space. But pressure 1 wants it more, okay? So everyone tries to get into that space, but pressure 1 is going to win, so the water continues to move forward. So the water in section 1 moves in there, and it moves this chunk of water along to the right into section 2. So delta x is this, because of course the amount of time where that work is going to be done is going to be crossing over the threshold from section 1 to section 2. Any other time it's moving, the pressure is the same on both sides. So what's A times delta X? Any ideas? It's the volume of my little mass, right? My little mass of water that I'm chasing around. So another way to think of the non-conservative work is it's the difference in the pressures on the two sides of the chunk of fluid times the volume. Well, that gives me an idea. I don't want to be beholden to the mass of my chunk nor the volume of my chunk, but I can solve those two problems all in one by dividing by this volume. So what does that do for me? Well, it'll get rid of the V that I just put in, and all the other terms have a mass in them, the mass of my chunk. So the mass of my chunk or the volume of my chunk individually seems kind of arbitrary, but the mass over the volume is what? It's the density, and that's a property of the fluid as a whole. It doesn't matter if you're talking about a little chunk or a big chunk. So just like that, my little test chunk that I was using for my development is going to go away. None of its properties survive. So just like that, I've gone from talking about one chunk of water to the fluid as a whole. So I have the density in there. That's something we can understand. Okay, we're working with water. It has this density. We have the speed of the water when it's in section 1. We have the height of it when it's in section 1. We have the pressure when it's in section 1. And we have all those things too when it's in section 2. So this is section 1, section 1, section 1, and then I'll double underline section 2. And so the only thing I will point out is that we have a wayward term there, P2. It's not with its friends on the other side. So let's fix that. We'll put this over here. Now we've got all the section 2 variables on one side and all the section 1 variables on the other side. And we've noticed something interesting. What do you notice about these things on both sides? It's the same exact set of stuff. We've just found a conserved quantity for a fluid. Let me write down this. We found that P plus 1/2 rho V squared plus rho GH is conserved for a fluid. I guess I'll put in parentheses for what's called an ideal fluid. So when I say ideal fluid, we have neglected several important features that could be going on. One of which is that you could have friction of the fluid with the walls of the container. So that is nowhere to be found. We also said there can be no turbulence or rotation. So there are several things that we neglected here. Okay? So when we say ideal fluid, we mean there's no fluid friction and no rotational flow. Both of which in and of themselves can have important applications in fluid flow in medicine or otherwise, but that's the nature of physics 1, is we can't get too much into this stuff. Okay? So no fluid friction with the walls of the container, also no fluid friction with itself. You may know that there's something called viscosity, right? Things like honey and syrup. They have just friction sliding on itself. Okay, so all these things we're neglecting right now to arrive at this conservation. And this is Bernoulli's principle, is that this quantity is conserved. So this is a good opportunity to look at what the heck all these terms are, so that we can understand what this is telling us. This thing right here, as you can probably see, is basically just a weird version of good old translational kinetic energy. It's just, instead of 1/2 mv squared, it's 1/2 density v squared. It's because we divided 1/2 mv squared by the volume. One way to think of it is that it's the kinetic energy per unit volume. Okay? So it's the translational kinetic energy contained per unit volume of the fluid. Another way to think of it would be like kinetic energy density, right? Instead of mass density, it's energy density. It's how much kinetic energy is contained per unit volume in the fluid. Okay? So fluid is kind of an amorphous thing, and where does it begin, where does it end? So it's a lot easier to talk about the kinetic energy contained per unit volume rather than worrying about how much total volume of fluid is going to pass through the system. So functionally, that works exactly the same as kinetic energy, except for it's a density in there, a rho in there instead of an m. Same thing with this one. This is your gravitational energy, potential energy per unit volume. Or if you prefer, potential energy density. So it's how much stored energy is in a fluid per unit volume. So that's all well and good. We've just tried to turn it into kinetic energy per unit volume, potential energy per unit volume. Units, of course, of those are, if you're talking about energy per volume, that would be joules per meter cubed, right? How many joules are contained per unit volume? And then coming out of seemingly left field, of course it wormed its way in here from the non-conservative work term, is a pressure. Okay? Pressure is not an energy at all. Okay? Pressure is how much force per area is exerted. So if you're in this fluid, how much pressure would be, or how much force would be acted upon a given area? Now, if your alarm bells go off, this was on your homework number 1 this semester, this idea that you can't add things that have unlike units, right? You can't add a second to a meter. It makes no sense. It has to be like units. You may wonder, how is this possible? Well, if you take pressure, we of course measured in pascals, which is force per area, newtons per meter squared. Well, that happens to be the same units as joules per meter cubed, because at this stage I can remind you that a joule is a newton meter, and that is going to reduce to the same units. So we have this kind of, I think, truly strange quantity that's conserved for a fluid. It's got 2 energy ingredients and one that is seemingly out of left field, the pressure. But nonetheless, for a fluid, if you add these 3 things up, you're going to get the same number. Okay? So remember that our density is not negotiable, so there's really only 3 active ingredients here. Pressure, speed, and height. Pressure, speed, and height. It's basically saying that these 3 things have an interrelationship. They can't all increase simultaneously, because if they did, this quantity wouldn't be conserved. They can't all decrease simultaneously, because then this quantity would not be conserved. If you know one increases and a second stays the same, the third one's going to have to decrease, right? If 2 of them increase, the third has to decrease. So you can say that they have some kind of relationship woven in. And what I want to talk about next is that this is some old stuff we already knew, kind of just repackaged in the energy format, and some new stuff that we may not have quite known yet. So let me go ahead and discuss that. Are there any questions before I clear a little space? Okay, so let me clear a little space. I'll tell you the old news and I'll tell you the new news. Let's start with the easiest stuff. First of all, let's hold the pressure constant. An easy pressure to hold constant to is atmospheric pressure, for example. Doesn't have to be held constant at atmospheric pressure, but that is typical for us, right? So this equation will tell us that if we go to a larger h value, what has to happen to V? Has to decrease. So this right here is old news. It's the oldest news. Let's say I have a garden hose and I spray water out of it, like this. As soon as it is out in the air, you can in a certain sense think that all of this water is at the surface, right? Atmosphere has immediate access to basically all of that water, so the pressure of that, as soon as you exit the hose, the pressure is all atmospheric. So we've taken atmospheric pressure, held it constant. That's basically not, nothing's happening with that. And this basically says when we go to a larger height, the fluid slows down. And of course, at the top of the flight, it's stopped. So we're just watching the same thing with water molecules as we observe with a baseball, right? So you throw a baseball up in the air, why does it slow down? The potential energy goes up, the kinetic energy goes down. We're just watching that with water molecules. So here the pressure term, which is kind of the new weird quantity, is kind of taken out of the situation, and we're just watching the two good old kinetic energy and potential energy trading. So that's old news. Water will slow down as you fire it into the air, just like any projectile. Let's let one of the other variables take a turn being constant. Let's let the speed have a chance being constant. So any constant value will do, but the easiest one for me is to hold it to 0 as an example. Because of course we have now at least one lecture's worth of experience with fluid that isn't moving. It's just staying still. So we can draw a body of water that's just sitting there. This tells us that if we go to a larger height, what happens to the pressure, or what must happen to the pressure? It has to decrease. So this is old news as well, because this H is good old potential energy H. We would set it to 0 at the lowest height of interest. And as we go to a larger height, above that, our pressure should decrease. And of course, the reason why is that if we go higher up, we're also going shallower, right? So the pressure should decrease because you're going to a shallower depth, okay? So H is not to be confused with D. D is measured down from the surface. And there, of course, when you go deeper, the pressure increases. We're now going to a larger height above the ground, and the pressure is going to decrease. So unless you can show me an upside-down lake where the surface is the lowest point, this is just saying that pressure increases with depth. This is just another way to say that, right? So we go to a larger height above the ground, we're going shallower in any body of water. So that's all old news. And really, the most exciting thing that comes out of Bernoulli's equation is if we hold the height constant. Because if we hold the height constant, we see that if you go faster, what does that imply about the pressure? So when fluid flows faster, this is counterintuitive, goes to lower pressure. Okay? So what the heck is going on here? Well, first of all that we've done with Bernoulli's quantity is take something that we knew before and couch it as a conservation. So if we had a larger pressure over here and a smaller pressure over here, this is a fight that the larger pressure is going to win. So this thing goes like this. So the force is, of course, in the direction of the lower pressure. And it's going to accelerate it and make it go faster. So we have a higher pressure in section 1, therefore we have a higher speed in section 2. So it's just couching that as a kind of a conservation. this idea that the fight between two pressures, the bigger pressure wins, we're now saying that the higher pressure in one section turns into a higher speed in the other section. Now, this is perhaps the most counterintuitive result because I might say you have a high pressure fire hose, right? So high pressure, you think of high pressure hose as outputting high speed fluid. So where do I get off saying that high speed is low pressure? Well, let me show you. So we have a fire hose. Its nozzle is narrow like that, specifically for the same reason as that finger on the end of a garden hose. Okay? So this is called a high pressure hose. It's not high pressure and high speed simultaneously. It's high pressure, so it can trade to high speed. Okay? So out here, we have basically atmospheric pressure. So now we have a pressure differential between the very high pressure inside the hose and atmospheric pressure outside, so we can trade that high pressure for high speed. So out here, it's at atmospheric pressure, but it's a very high speed. So the whole point of a high pressure hose is you can trade it to high speed. Okay? So exactly what I was saying is that when the fluid speed increases, the pressure drops. You're pushing out into the lower atmospheric pressure, so the fluid can speed up as a consequence. So now it's high speed. Well, if you're standing here and it hits you, you might not be very happy. It will, of course, if it hits you, it'll slow down and it'll trade the other way, right? If you lower the speed, the pressure goes back up again. So you will certainly experience a large pressure when it hits you. So it's high pressure in the hose. It's high pressure when it hits you, but it's high speed in transit. So you can trade between one and the other. Okay? So does that make sense? In fact, this is a good opportunity for me to talk about some applications that you may have seen in chemistry. Do you guys have those sinks in your chemistry labs that have like the nozzles like this? You turn them on and they spray everywhere, right? And the reason why I have the narrow nozzles is to get high speed water to come out, right? So it's basically very high speed fluid emerging into the atmospheric pressure. I don't know if you have more fancy devices now, but those very narrow nozzles with the ridges on them, they're made for suction. Do you guys still use for suction? So what you do is you have like a rubber tube or something with a little side outlet. Some people? Okay. So let's talk about how that works. So you have air molecules out here. So those air molecules are at approximately atmospheric pressure, and they're also at approximately 0. And of course, you probably well know that air molecules are not just hanging in the air, they're moving. But when I say 0, I mean 0 compared as a baseline. Whatever speed they're moving, I'm going to zero that out. So if I indulge in a tiny little bit of friction, which is not accounted for in Bernoulli's, but I'm just talking conceptually here, what happens is some of the water here comes by and causes these air molecules to move along with the stream. And what happens is that if you can speed up the fluid, which in this case the fluid is the air, you're going to drop the pressure. So the way to think of it is that if the fluid is not moving, the gas isn't moving in any particular direction, it's basically pushing out against the walls of the container. So here, it has a high pressure, atmospheric pressure in this case, when it has no net motion in any given direction. It just it pushes out in all directions because it's not doing any particular thing. But if we can get them to all move in a certain direction, or more in a certain direction, we can increase their speed. Now they don't push out uniformly in all directions anymore. So if we increase their speed in one direction, we drop their pressure. So what you do in chemistry is you kind of make yourself a little contraption like this, where it has a side outlet. You have the air molecules out here at atmospheric pressure, but here, because they're moving, you've dropped the pressure, and you can see you're going to get suction, right? Because the atmospheric pressure is going to push in here. So, like that, okay? So, our equations are definitely more appropriate for liquids. If I reference them in the homework for any gas, you're going to have to assume that the gas has uniform density. But if we loosen our restrictions a little bit, there's a lot of phenomena that come about here. This is just the first of several that I want to mention. So this idea that if you can get a fluid, whether that be a liquid or a gas, moving faster, its pressure drops. They're trading one for the other. Bernoulli's doesn't always explain why that exchange is occurring, but it just says that it has to follow.